Welcome! In this session, we'll explore LeetCode problem number 1130, minimum cost tree from leaf values. This problem challenges us to construct a binary tree in a way that minimizes the cost of its non-leaf nodes. Together, we'll break down the approach step by step and learn how to solve it efficiently. Let's dive in. In this problem, we are working with an array of positive integers called ARR. Each element in this array represents the value of a leaf node in a binary tree. The tree we construct will have a specific structure. Every node must either have 0 children, meaning it's a leaf node, or 2 children. For non-leaf nodes, their value is determined by taking the largest leaf value in their left subtree and multiplying it by the largest leaf value in their right subtree. Our goal is to find the smallest possible sum of all the non-leaf node values across any valid binary tree that can be built from this array. We can always assume that constructing such a tree is possible. The input will be the array ARR, and the output will be a single integer representing the minimum sum of all non-leaf nodes in the tree. Let's look at our first example to understand how the problem works. Suppose the input array is 6, 2, 4. To minimize the sum of non-leaf node values, we can build the tree as follows. First, we combine the leaf nodes 2 and 4 to create a non-leaf node. The value of this non-leaf node is calculated as 2 * 4 equals 8. After combining these two nodes, the remaining array becomes 6, 8. Next, we combine the nodes 6 and 8 to form another non-leaf node. The value of this node is calculated as 6 * 8 equals 48. This gives us a tree structure where the total sum of non-leaf nodes is determined by adding these two values. The total sum of the non-leaf nodes in the tree is 8 plus 48, which equals 32. This is the minimum possible sum for the given array, 6, 2, 4. Now, let's consider another example with a smaller input. If the input array is 4, 11, there is only one possible way to construct the tree. We combine 4 and 11 directly to form a single non-leaf node. The value of this non-leaf node is 4 * 11 equals 44. Since this is the only possible tree, the total sum of non-leaf nodes is simply 44. For a more complex example, let's take the input array 15, 13, 5, 3, 15. One way to minimize the sum is to start by combining the smallest values first. We combine 3 and 5 to form a non-leaf node with a value of 3 * 5 equals 15. This leaves us with the array 15, 13, 15, 15. Next, we combine the nodes 13 and 15 to create another non-leaf node with a value of 13 * 15 equals 195. The updated array becomes 15, 15, 195. Then, we combine the two 15s, forming yet another non-leaf node with a value of 15 * 15 equals 225. This reduces the array to 225, 195. Finally, we combine the remaining nodes 225 and 195 to create the root node of the tree. The value of this node is calculated as 225 plus 195 equals 500. Adding up all the non-leaf node values, we get 15 plus 195 plus 225 plus 500 equals 500 as the total sum. This is the minimum sum of non-leaf nodes for this input. With constraints on the array size and values, it's important to ensure that our solution is efficient. For example, with a maximum length of 40 and values up to 10,000, we need to avoid solutions that have exponential time complexity. Edge cases to consider include arrays with only 2 elements, where there's only one possible tree, and arrays with large values where computational efficiency becomes critical. To tackle the problem of constructing a binary tree that minimizes the sum of non-leaf node values, we first consider the brute force approach. Here, the idea is to try all possible ways of splitting the array into 2 parts, compute the cost for each split, and recursively solve the subproblems for the left and right subarrays. While this method is straightforward to implement, it quickly becomes computationally infeasible for larger arrays because the number of recursive calls grows exponentially, leading to a time complexity of O(2 to the power of n). Additionally, the recursion stack can go as deep as the size of the array, consuming O(n) space. This approach, though simple, is impractical for larger inputs because of its inefficiency. Next, we turn to a more optimized solution using dynamic programming. By breaking the problem into overlapping subproblems, we can store intermediate results to avoid redundant calculations. In this approach, we define a table, dp I, j, where each entry represents the minimum cost to construct a tree from the subarray ARR, ij plus 1. For a given subarray, we calculate the cost by trying all possible splits, combining the results of the two subarrays, and adding the product of the largest elements from each part. This reduces redundant calculations compared to brute force and provides a structured way to solve the problem. The dynamic programming solution, while significantly faster than brute force, still has its limitations. Its time complexity is O(n) cubed, as we iterate over all subarray ranges and splits, and the space complexity is O(n) squared, to store the dp table. This makes it more efficient for moderate input sizes but less practical for very large arrays due to the cubic time complexity. To address this, we explore the most optimal approach, a greedy algorithm using a monotonic stack. The key insight here is that the cost of merging two nodes is determined by the product of the largest values in adjacent subarrays. By always merging the smallest local pair first, we can minimize the overall cost. Using a monotonic decreasing stack, we process the array efficiently. At each step, while the current element is greater than or equal to the top of the stack, we pop the stack and compute the merge cost using the smaller of the current value or the next value in the stack. This ensures that we are always merging the smallest local pairs first. The monotonic stack allows this process to run in O(n) time, as each element is pushed and popped from the stack only once, and it requires O(n) space for the stack. This approach is highly efficient and well suited for large input sizes. Given the trade-offs of the approaches, we selected the greedy algorithm with a monotonic stack as the most optimal solution. While the dynamic programming method provides a more intuitive framework for solving the problem, its O(n) cubed complexity makes it impractical for larger arrays. The greedy approach, on the other hand, leverages the problem's structure to achieve a linear time solution. The essential insight here is that merging smaller local pairs first minimizes the total cost, and the monotonic stack efficiently identifies these pairs without needing to explicitly examine all possible subarray splits. This makes the greedy approach not only computationally efficient but also elegant in its simplicity. With its linear time complexity, minimal space usage, and scalability, it is the best choice for competitive programming and real-world applications. By focusing on the smallest local merges, this approach outperforms both the brute force and dynamic programming methods in terms of speed, efficiency, and practicality. In this problem, our goal is to minimize the sum of all non-leaf node values in a binary tree formed using a given array of leaf values. The value of each non-leaf node is determined by the product of the largest leaf values in its left and right subtrees. To achieve this, we need to determine the most efficient way to partition the array to minimize the total cost. The key to solving this problem lies in using a dynamic programming approach, which allows us to explore all possible partitions while storing intermediate results to avoid redundant calculations. First, we define the state, let dp I, j represent the minimum cost to construct a tree using the subarray ARR, ij plus 1. Additionally, we pre-compute a helper table, max_leaf, I, j, to store the maximum leaf value for each subarray. This avoids recalculating the maximum value for the same subarray multiple times, improving efficiency. Finally, we establish the base cases. When the subarray contains only one element, there are no non-leaf nodes, so the cost is 0. Similarly, the maximum value for a single element subarray is simply the value of that element. Now, we move on to the recursive transition. For any subarray ARR, ij plus 1, where I is less than j, we consider all possible ways to partition the array. Let k be the partition point, splitting the subarray into ARR, ik, for the left subtree and ARR, k plus 1 ej plus 1, for the right subtree. The cost of this partition is the sum of three terms: the cost of constructing the left subtree, the cost of constructing the right subtree, and the product of the maximum leaf values in the left and right subtrees. Mathematically, this is expressed as cost equals dp I, k, plus dp, k plus 1, j, plus max_leaf, I, k, asterisk max_leaf, k plus 1, j. To find the minimum cost for dp I, j, we iterate through all possible partitions and take the smallest cost. Additionally, we pre-compute the max_leaf values for all subarrays using a nested loop. For a subarray from index I to j, the maximum leaf value is simply the largest element in ARR, ij plus 1. This pre-computation step ensures that we can look up the maximum value in constant time during the main computation.
The next step is iterative computation. We process all possible subarray lengths, starting from length 2 and going up to the length of the entire array. For each subarray of the current length, we use the recursive relation to compute the minimum cost and update the DP table. Once all subarrays have been processed, the result is stored in DP 0 and 1, which represents the minimum cost to construct the tree using the entire array. There are several key insights in this approach. First, the problem can be divided into smaller subproblems by considering partitions within subarrays, and each subproblem can be solved independently. Second, the problem has an optimal substructure, meaning that the solution to a larger subarray can be built from the solutions to its smaller subarrays. Finally, pre-computing the max_leaf table significantly reduces complexity, as it eliminates the need to repeatedly calculate maximum values for the same subarrays. The data structures we use are the DP table, which stores the minimum cost for each subarray, and the max_leaf table, which stores the maximum leaf value for each subarray. Both tables have a size of n squared, where n is the length of the input array. Let's analyze the complexity of this approach. For the time complexity, pre-computing the max_leaf table requires n squared time, as we compute the maximum value for all subarrays. Filling the DP table involves iterating over all subarrays and calculating the minimum cost for each partition. For a subarray of length L, we perform L operations, and summing over all lengths gives a total complexity of n cubed. Thus, the overall time complexity is n cubed. The space complexity is n squared, since we store both the DP and max_leaf tables. We also need to consider edge cases. For a single element array, the cost is 0 because there are no non-leaf nodes. For a two-element array, there is only one possible tree, so the cost is simply the product of the two elements. Finally, for large arrays, we ensure that the solution remains efficient even for the upper limit of 40 elements, leveraging the pre-computations in dynamic programming structure to handle the input size effectively. Let's look at an example to better understand the execution. Suppose the input array is ARR equals 6, 2, 4. First, we pre-compute the max_leaf values. For the subarray 6, 2, the maximum value is 6. 4, 2, 4, the maximum is 4. For the entire array 6, 2, 4, the maximum is again 6. Next, we compute the DP values. For the subarray 6, 2, the cost is the product of the two elements, which is 6*2 equals 12. For 2, 4, the cost is 2*4 equals 8. Finally, for the entire array 6, 2, 4, we calculate the minimum cost by considering all possible partitions. Using the formula, the result is DP 0, 2 equals 32. Thus, the minimum cost to construct the tree is 32. This example demonstrates how the algorithm efficiently combines pre-computed values in dynamic programming to arrive at the optimal solution. This Python implementation solves LeetCode problem number 1130, minimum cost tree from leaf values, using a greedy stack-based approach. The goal is to minimize the sum of all non-leaf node values in a binary tree constructed using the given array. The MCT from leaf values function starts by initializing a stack with float, INF, as a sentinel value. This ensures no boundary issues when comparing elements. The result variable is initialized to store the running total cost of the tree. We iterate through each number in the input array ARR. For each number, if the top of the stack is smaller than or equal to the current number, we pop the top element, representing the smallest value. The cost of merging this value is added to the result by multiplying it with the smaller of the adjacent values, the new top of the stack or the current number. This ensures we minimize the cost of merging at every step. After processing, the current number is pushed onto the stack. Once all numbers are processed, the stack may still contain elements that need merging. We process these remaining elements by repeatedly popping the top value and combining it with the next top value, adding the product to the result. This continues until only the sentinel value and one element remain. The function returns the total result, which represents the minimum cost to build the tree.
The algorithm is efficient with a time complexity of O(n), because each element is pushed and popped from the stack at most once, ensuring optimal performance for this problem. Here, we begin by importing the necessary libraries and defining our class, solution, where the method MCT from leaf values is implemented. This method calculates the minimum cost to build a tree from leaf values using a stack-based greedy approach. First, we create a stack and initialize it with a sentinel value, integer.max_value, to handle edge cases. We also define a variable result to accumulate the total cost. Next, we iterate through the input array ARR. For each element, we check if the top of the stack is less than or equal to the current number. If it is, this means we need to pop the stack and calculate the intermediate cost by multiplying the popped value with the smaller of its neighbors, which are the current number and the new top of the stack. This ensures we are always minimizing the cost. After processing the current number, it is pushed onto the stack to be considered for future calculations. After processing all elements in the array, we might still have some values left in the stack. To handle this, we continue popping elements from the stack while ensuring the sentinel value remains. For each pop, we add the product of the popped value and the new top of the stack to the result, thereby finalizing the cost. Once all calculations are complete, the result is returned. In the main method, we demonstrate the functionality by creating an instance of the solution class and using the example input, 6, 2, 4. When we call MCT from leaf values with this input, it calculates and prints the output, which is 32. This represents the minimum cost to construct the tree for the given leaf values. To start solving the problem, we initialize our stack with a sentinel value of infinity and set the result to 0. This setup helps us manage the comparisons and calculations as we process the array. First, we encounter the value 6. Since the stack currently only contains infinity, we simply append 6 to it. The stack now contains INF 6. Next, we process the value 2. Similarly, since 2 is smaller than the top of the stack, we append it directly. The stack becomes INF 6, 2. These initial steps prepare the stack for efficient processing of subsequent elements. As we process the value 4, we notice that the top of the stack, 2, is smaller than 4. This means we can calculate the product for the subtree rooted at 2. Popping 2 from the stack, we update the result by adding 2 min 6, 4, which equals 8. The stack now becomes INF 6. Next, we append 4 to the stack, resulting in INF 6, 4. In the final processing step, we pop 4 and calculate 4 6, which adds 24 to the result. The stack reduces to INF 6. Finally, we pop 6, but since we multiply it by infinity, this step is ignored due to the sentinel. The total result is 8 plus 24 equals 32. In this example, we start with the same initialization, a stack containing infinity and a result of 0. As we process the first value, 4, we append it to the stack. The stack now looks like INF 4. Next, we process 11. Since the top of the stack, 4, is smaller than 11, we pop 4 and calculate 4 min INF 11, which equals 44. The result is updated to 44, and the stack now contains INF. We then append 11 to the stack, making it INF 11. After processing 11, we move to the value 3. Since 3 is smaller than the top of the stack, we append it directly. The stack now becomes INF 11, 3. Next, we process the value 2. Here, the top of the stack, 3, is greater than 2. So, we pop 3 and calculate 3 min 11, 2, which equals 6. We add this to the result, updating it to 50, and the stack becomes INF 11. We then append 2, resulting in INF 11, 2. In the final processing step, we pop 2 and calculate 2 11, adding 22 to the result. The stack reduces to INF 11. Finally, we pop 11, but as it's multiplied by infinity, this step is ignored. The total result is 44 plus 6 plus 22 equals 72. For this example, we again initialize the stack with infinity and set the result to 0. Processing begins with the value 1, which we append to the stack. The stack now looks like INF 1. Next, we process the value 2. Since 1 is smaller than 2, we pop 1 and calculate 1 asterisk min INF 2, which equals 2. We add this to the result, updating it to 2, and the stack becomes INF. We then append 2 to the stack, making it INF 2. Now, we process the value 3. Since 2 is smaller than 3, we pop 2 and calculate 2 asterisk min INF 3, which equals 6. Adding this to the result gives an updated total of 8, and the stack becomes INF. We then append 3 to the stack, resulting in INF 3. Next, we process the value 4. Here, 3 is smaller than 4, so we pop 3 and calculate 3 asterisk min INF 4, which equals 12. Adding this to the result gives a total of 20. The stack reduces to INF, and we append 4 to it, making INF 4. In the final processing step, we pop 4, but since it's multiplied by infinity, this step is ignored. The total result is 2 plus 6 plus 12 equals 20. The time complexity of our solution is O, n, where n represents the size of the input array.
This is primarily due to the way we process elements in the array using loops.
First, the outer loop iterates over each element of the array exactly once, contributing O, n, iterations. Within this loop, there's a while loop that processes the stack. The key observation here is that each element of the array is pushed onto the stack once and popped from the stack at most once. This means that the total number of iterations of the while loop, across all elements, is also bounded by O, n.
After the main loop finishes, there is a second while loop that handles any remaining elements in the stack.
Since each element is popped only once here as well, this cleanup step contributes another O, n. When you combine these together, the total number of operations remains O, n. By summing up the contributions from the outer loop, the inner while loop, and the final cleanup, the overall time complexity of the algorithm is O, n. What's important to note is that this linear time complexity holds true across all cases, whether the input array is sorted in ascending order, descending order, or is in a random order. This is because each element is always pushed onto the stack once and popped at most once, regardless of the order of the array. Moving on to space complexity, the algorithm's space usage is also O, n. The primary contributor here is the stack, which temporarily stores elements from the array as they are processed. In the worst-case scenario, such as when the array is strictly decreasing, the stack will hold all n elements at once. Aside from the stack, the algorithm uses only a constant amount of memory for variables like the result and loop counters, which is O, 1. When we combine these factors, the overall space complexity of the solution is O, n, dominated by the stack. To understand the efficiency of this approach, let's compare it to a brute force method. A brute force approach might involve recursively generating all possible binary trees and calculating their costs. This would take exponential time, O, 2 to the power of n, as it explores all possible combinations, making it impractical for larger inputs. In contrast, the stack-based greedy approach achieves O, n, time complexity by processing each element in the array exactly once and efficiently determining the minimum cost without explicitly constructing all trees. This is why the greedy approach is so effective. Each element is pushed and popped from the stack just once, with the total operations scaling linearly with the size of the array. To summarize, the algorithm achieves a time complexity of O, n, and a space complexity of O, n, offering a significant improvement over exponential solutions by leveraging the stack-based greedy strategy. When tackling this problem, there are several common mistakes to be aware of. First, misunderstanding the problem statement can lead to confusion. Remember, the goal is not to minimize the product of the leaf values but rather to minimize the sum of all non-leaf nodes. These non-leaf nodes are calculated as the product of the two largest adjacent elements during each split, so the focus should be on how you structure those splits. Another frequent error is relying on a brute force approach without optimization. Recursively trying all possible splits without memoization results in exponential time complexity, which is impractical for larger inputs. Additionally, some might incorrectly assume that the largest value must always appear in the final split. While larger values do contribute significantly to the product, the order and positioning of splits are what ultimately determine the total cost. Be cautious to only form non-leaf nodes from adjacent elements, as ignoring this adjacency constraint can lead to invalid results.
Finally, don't overlook edge cases.
Arrays with only two elements, cases where all elements are equal, or inputs with very large numbers should be thoroughly tested to ensure your solution is robust and handles all scenarios correctly.
Now, let's delve into some insights that are particularly useful for interviews.
For this problem, the optimal solution relies on a greedy approach using a monotonic decreasing stack. This method is not only elegant but also highly efficient, with a time complexity of O(n). It works by simulating the process of splitting elements in a greedy manner, ensuring that local decisions lead to the global minimum cost. While dynamic programming provides a more intuitive framework for solving this problem, its O(n)³ complexity becomes a bottleneck for larger inputs. The stack-based approach, in contrast, is both faster and more space-efficient. You should also be ready to explain why the greedy method is effective here, particularly how it leverages adjacency and local optimality. Additionally, this problem demonstrates a pattern of breaking complex tasks into smaller subproblems, a strategy that is common in greedy and partitioning problems. Lastly, paying attention to edge cases is critical. For example, you should explain how your solution handles arrays with only two elements or arrays where all elements are identical. This level of detail shows your thoroughness and ability to anticipate edge scenarios. This problem shares similarities with several others, making it an excellent opportunity to discuss related concepts. For instance, LeetCode 1007, minimum domino rotations for equal row, also involves a greedy approach to minimize operations. Similarly, LeetCode 312, burst balloons, focuses on partitioning but uses dynamic programming to find the optimal solution. Another related problem is LeetCode 1547, minimum cost to cut a stick, which deals with splitting segments in the most efficient way. Finally, LeetCode 1167, minimum cost to connect sticks, emphasizes minimizing costs through specific greedy decisions. Beyond related problems, it's helpful to evaluate alternative approaches and their trade-offs. A dynamic programming solution, with its O(n)³ complexity, is intuitive and easier to debug but becomes computationally expensive for larger inputs. On the other hand, the greedy approach with a monotonic stack is the most efficient at O(n), but it can be harder to derive during an interview without prior exposure. Recursion with memoization strikes a balance, offering a time complexity of O(n²). It avoids redundant calculations while remaining conceptually simpler than pure DP. Understanding these trade-offs and articulating them effectively can make a strong impression in an interview setting. Thanks for joining me on this walkthrough of the minimum cost tree from leaf values problem. We reviewed the dynamic programming approach and key takeaways for solving such optimization problems. Keep practicing and applying these strategies to similar challenges. Don't forget to like, subscribe, and stay tuned for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!